Okay, now let's talk about differentials. Differentials and linear approximation are flip sides of the same coin. Like mathematically, writing out the calculus, it looks like we're doing something different, but we're really kind of not. So the naive way to think of a differential is literally the definition of the derivative written in Leibniz notation. dy dx equals f prime. Like that's just notation there. There's no math there. These mean the same thing. This is what we call prime notation. This is what we call Leibniz notation. Now, naively, we could pretend that we're multiplying the dx to the other side. This is not a fraction. dy dx is not a fraction of differentials. That is not divided. This is one single symbol here. But let's pretend it is. Let's pretend that that's a fraction of differentials. And let's pretend that we could multiply the dx to the other side. That would give us this expression here. That's what a differential is. This says that a very small change in y is equal to the derivative at some value times a small change in x. And when I say small, I mean as the limit of delta x goes to 0. So we have actual change delta y, the actual change in y is approximately equal to the derivative at some value times your change in x. So we've got some function. We're at some value here, calling it x. I want to go up by some delta x. I want to look at some other function value that's going to give me, here's my original f of x, here's my f of x plus delta x, my next y value. This change in y is approximately equal to the slope of this tangent line right here, the derivative times change in x. Because that's what slope is. Slope is over by change in x, up by change in y. Rise over run. Now you can see in my picture here, this is not the same as this distance. That's why it's approximate. But if delta x is really, really small, then this delta y will be really small, and this approximate in the limit becomes equal. Well, when we take the limit as delta x goes to 0, then that delta y becomes a dy, that approximate becomes an equals to, and that dx or delta x becomes a dx. So we call this the differential of a function. So if I had, say, y equals x squared, then dy would be, take this guy's derivative, 2x, and multiply by dx. That's it. You take the derivative and you write a dx beside it. Algebraically, it's kind of the same as saying y prime equals 2x. Well, what's another name for y prime? dy dx. Like that's just taking the derivative, right? And then kind of pretending like you've pulled this dx up here. So you can algebraically, you can pretend that you just took a derivative and then you multiplied the dx over. It's not really what's happening. What's happening is all this stuff I said up here. It's a linear approximation. When then we take the limit as delta x goes to 0. None of that matters. When you're finding a differential, you take the derivative and you write down dx and you're done. If you have y equals tangent of x, then the differential dy is take that guy's derivative with respect to x, secant squared of x, and then write a dx. That is the differential. It's not the derivative. That's the derivative. The differential dy is secant squared of x dx. And we'll do, or here's that same picture I was just drawing. So what we're estimating here is not a new function value, but a change in function value. Delta y here is the actual change in y values from that point to that point. Delta x is the actual change in x's. And we're saying that the actual change is approximately equal to the change in y on my tangent line. Okay. Stop that one.